The accelerated verification of NAND flash memory using hardware emulator. In NAND flash memory, logic design becomes more complex as generations go by, and verification test cases are also increasing. In order to overcome the above situation, a verification methodology using an emulator rather than a Verilog simulator is needed. So the logic design of NAND flash memory is composed of RTL only, but also includes analog behavior model and bidirectional transistors. In addition, NAND flash memory also needs a core model that is made for checking cell operations. In this paper, emulation using a Cadence PZ2 emulator is proposed in NAND flash memory, designing various design types such as transistors, gates, and analog behavior models. In order to improve the emulation speed, test bench optimization, interface signal minimization between test bench and DUT, and transaction-based acceleration (TBA) were applied to a previous simulation environment. As a result, the accelerated emulator improves the verification speed by more than 100 times compared to the Verilog simulator. Using the emulator verification environment enables verification of many test cases in a limited verification period, and the NAND flash memory operation at the system level is also verified. It will be the best solution for flash memory verification process. Introduction. Recently, features required for NAND flash memory are increasing, while the period of development and verification has not changed much. Whenever a new algorithm is developed, number of verification test cases is exponentially increasing. So in a given verification period, it's become harder to verify all test cases because of limited simulation resources and a few test cases that require very long simulation time. We adopted hardware emulation not only to reduce regression turnaround time, but to verify more complicated behaviors of NAND flash memory. But our device under test, DUT, was consist of various design styles, that is RTL, gates, transistors, and analog behavior model. In this paper, we introduced what were difficult points to set up a hardware emulation environment for our designs and how we solve it. 2. Emulator setup for flash memory. 1. Synthesizable model development of various design styles. NAND flash memory is not only designed with RTL, but consists of transistor and analog behavior models that are not suitable for emulation synthesis. Therefore, it is necessary to change them to synthesizable components and check final emulation correctly operating. 1-1. Change the bidirectional transistor to unidirectional. Because trans if 0 and trans if 1 are supported in emulator, the direction must be changed correctly to use nmos and pmos. For example, as shown in figure 1, transistors using trans if 1 do not need to distinguish between the source and drain, so most transistor level designs are likely to be designed without considering the part, so it is necessary to check the part and modify its nmos and pmos according to the correct direction. 1-2. Change some directional ports to unidirectional. Emulator cannot handle the sharp delay in Verilog's language. In the case of the bidirectional port controlled by sharp delay, these ports must be separated. For example, in some analog units, feedback loops can be formed by an port, which will be shown in figure 2 below. In simulation, the precedence relationship is clear due to sharp delay, but in emulator, it will be synthesized without delay. It will be called malfunction. As shown in the figure example, it can be solved by D flip-flop. The figure 2 is how to change using the bidirectional port. 1-3. Create or change synthesizable code for analog unit. Many non-synthesizable behavior model, that is the delay unit, pump, or voltage generator, are used in simulation. For example, delay unit, delay 10 nanometer, will be described as follows. It cannot be operated on emulator, therefore that many delay operation was performed using the counter. Figure 3. Example of non-synthesizable code converted to synthesizable code. 1-4. Remove multi-driving signal. Some multi-driving signals caused malfunctions in the emulator in order to increase the driving ability when designing. Multiple outputs can be designed to drive the same signal. The emulator does not support multi-driving, so only one output of the circuit must be connected to or gate must be connected to the higher level. Figure 4. Figure 4 is example multiple driving netlist and converted netlist. 2. Core operation behavior model. NAND Flash core is modeled to describe the behavior of data stored and read and also to be determined whether the NAND Flash operation is normal. It is composed of the memory cell and the data latch that is designed with several non-synthesizable 6T SRAM structures per line. Memory cell modeling has a problem with synthesizing when implementing all word lines and bit lines because it needs more than 100 gigabytes registers. In addition to describe the NAND Flash operation, the width of each cell was modeled. So the data latch model. Figure 5 is a circuit that a single page buffer and it models the Verilog code. So this is a simple method can be simulated that a page buffer, so it is not compatible for synthesis. Figure 5 is page buffer circuit and B is non-synthesizable code of page buffer. A new scheduler module was designed to implement the asynchronous operation of data latches, which made it synthesizable. The synchronizer and a scheduler module synchronizes the asynchronous control signals such as precharge, mon-s, set_s, reset_s to clock and reset. In addition, the retimer makes synchronizer output signals mutually exclusive. Figure 5 is a new scheduler module. So the memory cell modeling. The storage space required to model memory cell is number of blocks, x words line x, string x, bit line bit. The logic size is reduced by the using RAM provided by the emulator instead of synthesizing memory cells with gates and flip-flops. Memory cells are programmed the data from the page buffer by prefer, and so on the contrary, the read command transfer data from the memory cell to the page buffer. The stored value in memory cell buffer model indicates the programmed cell with a 0 and erased cell with 1. V-thread modeling. NAND flash memory is non-volatile data storage that stores the information by verifying the V-threshold of floating gate transistor device. One dimension with 16 bits was added to the memory cell model, and the V-threshold value of each memory cell was modeled in order to verify the detailed memory cell behaviors. However, the V-thread cell model that is implemented is too large to synthesize from the emulator to logic, so the following methods are applied. Figure 7 shows how to operate the V-thread cell models. The left is a part of the operated behavior and the right side is operated in the software. Erase program read processor calculates the V-threshold value and writes it to the V-threshold cell model pointed to the index. Figure 6 is the V-threshold modeling implementation method. 3. Emulation performance improved skills. After making a synthesizable model using above 1 and 2 steps, the performance of the emulation is improved by more than 5 times compared to the simulation. In order to maximize the performance of emulation, several skills were adopted. 3-1 is pulse reduction. The simulator performs the signal communication with each other using the DUT environment interface module in the software environment. Figure 8. So however, for verification using an emulator, communication connection between the UVM interface and the emulator interfaces, that is, interface connection between software and hardware, is required. Figure 9. The figure 7 is simulated test environment, and figure 8 is emulator test environment. So the NAND Flash basically has pins such as I/O, ALE, and CLE, and uses them to recognize CMD and operate like a transition level. However, NAND Flash has numerous operation options, so a lot of ports had been connected between the simulator and emulator for verification. And if the assertion is declared to the UVM, the port will be required for a checker. But this is one of the reasons to slow down emulation performance when the communicating between the simulator and the emulator. The status of all ports is transmitted after storing them in the temporary memory to check the state of all connected ports whenever one port moves. Therefore, the signal related operational option has been changed to change the force in the corresponding node when performing the emulation, and the assertion can be described and used inside the emulator DUT, and the necessary signals were changed so that they could be synthesized in the time module. As a result, more than 5 times the runtime has been improved by optimization the larger number of ports. 3-2 Direct register memory access. The I/O data path consists of the buffers latches that are transformed to the register according to the timing. It is more accurate to verify this operation than a simulation that reflects the timing than to verify verifying it in the emulator. To reduce communication between simulator and emulator, the direct register access method is used for a write and read operation instead of data in-out behavior using I/O ports. That is figure 9. Figure 9 direct register memory access. And we've used to set presets for unnecessary duplicate verification. It had led to an effect in improving the emulator speed more than 4 times. 3. Experimental result. To verify NAND Flash, millions of case verification are required. To compare simulation and emulation speed, we selected 5,000 test cases and summarized each runtime as follows, including the application of the method to increase performance described above. Also, it has a similar effect to interface optimization by insertion checker movement. Table 1 is runtime comparison, total cases 5,000. Table 2 just summarizes the emulation performance compared to simulation. Because design changes modification were frequently occurred in the development stage, compile time was also one of the important factors in this evaluation. Although the emulation's compile time is about 8 times slower than simulation, runtime and dump time of the emulation are 101 times and 18 times faster, respectively. The summary: by configuring the emulation verification environment, it's possible to verify more complex flash memory behaviors within the same period. So it's just thought it is very useful verification methodology as a replacement means of functional verification and long-time simulation. As long-time simulation is possible through the emulator verification environment, it's expected that an NAND operation at the system level can be verified in advance. Okay, thank you for your time. See you next time. I read the accelerated verification of NAND flash memory using hardware emulator.